So it's my pleasure to introduce tonight's speaker. Trevor Atkinson is a research scientist at the Idaho National Laboratory, where we just had a wonderful field trip. Hopefully we can do another one next year to reactors. He performs research in geologic design modeling to evaluate geological properties associated with movement, heat transfers, water transport, and solid mechanics of geologic systems. Work supports field and lab activities within the geothermal energy and subsurface systems. We run hydrothermal, water rock interaction experiments to better understand geothermal and heat storage potential, as well as carbon storage, carbon capture potential, and gradeside carbon mineralization. Before joining INL, Trevor was an environmental scientist at the Idaho Department of Environmental Quality. Did groundwater sampling analysis, government officials and subcontractors for INL's oversight program. Trevor has a master's from Utah State, Logan, and a bachelor's in geology from BYU Rexburg. Please join me in welcoming tonight's speaker, Trevor Atkinson.
Didn't want to turn your video on.
Turn my video on. Okay, let me stop sharing real quick. All right, thanks everybody. I'm going to turn my video on for the Zoomers here. Yeah. Okay. All right, thanks everybody. Thanks for your patience. Again, sorry. Thanks for having me. My name is Trevor Atkinson. I come from the Idaho National Lab, as was described, and I work in the geothermal energy and subsurface systems group. Is it not loud enough? It's dangling too far away from my mouth. Okay, let's do this. All right, we're good now. I work in the geothermal energy and subsurface systems group at the Idaho National Lab, and we belong to the Energy, Environment, Science, and Technology Directorate, which I'll get into in just a minute. But what I want to emphasize here is that what I'm sharing with you tonight is a compilation of three main topics, but it represents the research done over the last, 20 years, pieces of the research, not all the research that we've done, but pieces of the research we've done over the last 20 years. And I say we because none of this is mine solely, and it represents multiple researchers, including others that don't work at the Idaho National Lab. We do a lot of collaborative work with other national labs, and I'll get into that in just a minute. But the main three topics I'm going to describe today include geothermal energy, geologic thermal energy storage, and carbon sequestration. So a question before asked about where the top left photo is. That's Shoshone Falls down near Twin Falls, Idaho, in the Snake River Gorge. And then we've got an image on the middle there of an SEM image, scanning electron microscope image of a sand grain with some calcite growing on its surface. And then the bottom left is my geothermal photo from Iceland. That's geyser, the geyser for which all geysers are named. So here's an outline of my talk here. I'm going to start describing a little bit more about the Idaho National Lab and describing what we do, why we do it, and where we're at. I'll get into geothermal energy after that. And then I'll describe some of the more recent work we've done with geologic thermal energy storage. And then I'll finish up with carbon storage via mineralization or mineral carbonation. And then I have one slide on future directions that we're going to we're going to investigate in the near future. So where is the Idaho National Lab? You guys, you had a field trip down there, I hear?
Yes, recently.
When was that?
About 7 or 8 weeks.
Oh, nice. Didn't make it out to the reactor, I hear, though?
Third field trips on the reactor. This was just in the labs in Idaho Falls.
Okay.
Other times we've been in lava tubes.
Nice.
Oh,
Yeah, that's fun. Awesome. Good. So you basically know where this is, but I wanted to include it here just for those online and others who don't know where the Idaho National Lab is. So back in the 50s, the late 50s, the National Reactor Testing Station was developed and established out there in the desert of central Snake River Plain of southeast Idaho. And some of the firsts that we can describe here are this is where the first nuclear power plant was built and nuclear energy was produced and delivered to a nearby town. The Idaho National Lab is a DOE funded institution, and most of the work we do is funded by nuclear energy and other renewable energy offices at the National Lab. I said 1959, didn't I? This is 1949, correct. 1949 is when the Atomic Energy Commission established this area. So now the importance of this area is that we've had much testing done on all types of nuclear reactors. There's been, I think, over 50 nuclear reactors, 52 or 53 reactors that have been brought in and tested under various conditions. And this is the main reason why nuclear energy has been successful globally over the years, is based on researchers and their time spent on all these different reactors that have happened out in the Idaho National Lab. So at the Idaho National Lab, we, research development and demonstration is the bread and butter of what we do. Our mission and vision revolve around energy, critical infrastructure, and the future of the energy industry. Clean energy options and nuclear solutions are key pieces of the puzzle that we are solving at the Idaho National Lab. And the values, as you can see on the right-hand side, are similar to most that you might be aware of at other companies, but excellence, inclusivity, integrity, ownership, teamwork, and safety are the values on which we operate. So the Idaho National Lab, as described earlier, is in southeast Idaho, and we're the headquarters is in Idaho Falls, Idaho, where you guys all visited, but then the main chunk of the work that the INL does is out in the desert, about 50 miles to the west. And out there are 4 operating nuclear reactors, 1 main test reactor, and 3 other smaller reactors that do a variety of tests. We sit on about 890 square miles out in the desert, and then the additional land in the Idaho Falls. Right now, we're a little over 6,000 employees, and we operate on close to $2 billion. This is an FY22 number there, but right now it's about $2 billion a year. So at the Idaho National Lab, there are 5 directorates across the laboratory, and you can see those 5 listed here. The Nuclear Science and Technology is a big one, as well as the Advanced Test Reactor Complex, where a lot of nuclear research happens. Materials and Fuels Complex. This is where a lot of the materials and fuels that are generated, used, analyzed, destroyed, rebuilt, reanalyzed happens. And this is where a lot of the research for space batteries, so thermonuclear generators that go on the different Mars rovers and probes that go out into space. This is where those are developed. I belong to the second to the left on the Energy, Environment, and Science and Technology. And that's where we do basically anything related to those topics. And my research is focused on renewable energies. And then the National and Homeland Security Science and Technology Directorate focuses more on cybersecurity, homeland security, and other topics. Again, since nuclear is a big part of what the INL does, I'd be wrong to not highlight a few more areas of this research. This includes new nuclear materials and fuels, high performance computing for advanced modeling and simulations, national nuclear energy strategic infrastructure, powering science exploration, as I was just describing, and the research and development of next generation fuels. And that I believe is a TRISO or TRISO particle. Okay, so enough about the Idaho National Lab. Let's get into some of the topics for which we're all here. And the first, which is going to be geothermal energy. And then I'll get into these other types following that. Yes.
That sidewalk.
Yeah. Can we get there now?
No.
Perfect.
Perfect.
Thank you. Okay, so some geothermal energy basics. Let me get a show of hands just here in the room here. Who's a geologist? 1, 2, 3. All right, great. So now I know kind of where to focus here. So geology, I'm a geologist, I'm a research geologist. I do a lot of different things, but one of my interests and passions is in geothermal energy. Why? Why is geothermal energy important? What is geothermal energy? Well, the Earth is hot. The Earth is, the center of the Earth, it's about as hot as the surface of the sun, about 6,000 degrees Celsius. And, but why? Why is it so hot in the subsurface, in the core, I guess? It's because of two main sources. These could be debated, and I'm sure many will have other thoughts, but primordial accretionary heat that was built up as the Earth was being accreted, rocks hitting each other from space over time, and building of the planet created a lot of heat that later became insulated by additional accretion, and that heat is being stored in the center of the Earth. Radioactive decay is another form of that heat that we see, and through time, radioactive elements in the crust, in the center of the Earth, and then into the crust, that heat gets delivered toward the surface, and it's our job to find it and to be able to produce energy from it. So if anybody's interested in learning more about what the DOE has said about geothermal energy, there was a report which we contributed to in 2019 called GeoVision, and I'd invite you to go find that and take a look. It's got some really interesting stuff. And the image you're looking at here, I didn't state it yet, but is a heat flow map of the Earth, meaning, excuse me, of the US, and essentially showing heat coming from the Earth, and where it's hottest, where it's not so hot, and the color bar you can see red being hotter, green being coolest. And we're located relatively closely now here in Jackson to that bright purple spot, Yellowstone. And so we can see that Idaho itself is quite hot or has a lot of heat flow. And so we want to do at the National Lab is to understand many types of geothermal energy and how Idaho is special. Yes. It's the depth of this map that was chosen. Oh, I'm sorry. The question was, is there a reason why 7 kilometers was chosen? I'm sure there's a reason why these researchers, Blackwell and others, chose 7 kilometers, but they have different depths maps out there as well. I think there's 1 kilometer, there's 2, there's 5, there's 6, there's 10. This is just the one I chose, 7 kilometers. I better speed some of this up. Okay. So another slide on geothermal energy basics. In geothermal energy, we're focused on 3 main types. We've got shallow geothermal, which we can utilize with heat pumps, geothermal heat pumps. We've got hydrothermal geothermal, which is more of a conventional type of geothermal where there's fluids in the subsurface circulating, and we're able to drill into the surface or subsurface and access those fluids, pump them up and use them for energy and heating, and then later re-inject them for reservoir sustainability, and then circulate that type of system over time for energy production. The third type is quite new, but the DOE is highly interested in it. It's the top right, which is being blocked by talking Trevor Atkinson. It says enhanced geothermal systems. I guess I have it on the left too. But anyway, this is essentially areas where the rock is hot, but there's no fluids and no pathways for those fluids. And so essentially they're engineered systems where you can go down, stimulate the reservoir, break the rock open, and create fractures for fluids to be able to circulate in really hot, more hot or hotter than hydrothermal, than the traditional hydrothermal. And so that's an area that DOE is really interested in. And the US is the leader in geothermal energy production with, right now, I think it's over 4 gigawatts of geothermal energy production in this nation alone. So why geothermal in Idaho? Why do we focus on it? Why are we interested in it at Idaho National Lab? Well, the southern portion of Idaho is the Snake River Plain, where we understand that to be the track of the Yellowstone hotspot. So as the Yellowstone hotspot sat beneath North America, moving to the southwest, the volcanism that produced it, or that it produced, later left a scar on southern Idaho, and we call that the Snake River Plain. Well, this area has also been extensively studied, and we understand it to have extensive amounts of water, the Eastern Snake River Plain aquifer, and there's a lot of different reasons why we are interested in the Snake River Plain as a geothermal resource, but its proximity and the relic heat left over from Yellowstone is one of those. And we understand a lot of what the subsurface has to offer in the Snake River Plain due to lots of deep wells that have been drilled, and the high heat flow that we've been talking about in the previous slides. And then on the bottom portion of the screen here is a cartoon showing the nature of the Snake River Plain, where we've got a geothermal reservoir sitting beneath all the basalt flows. Like if you took a cut through the earth, this is what you might notice and see: basalt rocks, mafic basalt rocks that have erupted over millions of years, that are insulating the geothermal system existing beneath. One of the hardest parts about geothermal in southern Idaho is the blue that you see there, which represents the Eastern Snake River Plain aquifer, which masks much of that heat that could be used for geothermal energy. But our job is to try and find ways to see through that reservoir and to understand what is possible with geothermal. So at INL, we've been involved with decades of geothermal research. In the 70s, the INL led and developed the Raft River geothermal plant, the only geothermal plant in Idaho. And this is producing 13 megawatts, which is quite small compared to most, but it's been quite a interesting project to be involved with over the years. So in '79, they also led the first geothermal well stimulation program in the world, and this stimulation was successful and led to increased production at this plant. We're also involved in the design, construction, and operation of the first binary cycle plant, which means a two-fluid cycle plant where you pump up heat from the subsurface, pass it through another working fluid, and that fluid flashes to steam, and then that produces the power. And this was one of the first systems developed of those types. So again, here's another map, but a bit different color scheme of heat flow of the western United States. The Snake River Plain is located along the track of the Yellowstone hotspot. It's got some of the highest heat flow in the nation, up to 110 milliwatts per square meter. But why don't we see those temperatures at the surface? We do see quite a few hot springs in Idaho and in southern Idaho, but in the central of the plain, we don't. And that's likely because of the thick packages of basalt that exist in the Snake River Plain and the Eastern Snake River Plain aquifer, which masks a lot of the heat that might be present in the subsurface. But again, our job is to see how we can find those heat signals and understand where and how we can take advantage of those things. Oh, and the southern Idaho has been identified as an area for high EGS potential, EGS being, again, enhanced geothermal systems. So here's another map of southern Idaho looking at the Eastern Snake River Plain temperatures. I know the contours might not be as easily visible, but they range from red to yellow to green. And they range from about 9 degrees to 20 degrees. Now, that's not very hot, but those are temperatures of the Snake River Plain aquifer. Those are the cold water temperatures which enter the Snake River Plain up on the Yellowstone Plateau and percolate through the ground all the way down toward Twin Falls, Idaho, where they exit at Thousand Springs. So there's a thick package of basalts that are saturated with this cold water, and any heat that we are looking for is easily masked by that aquifer. Now, let's see. So the image you see on the left, that's a theoretical cross section showing cold temperatures or cold water temperatures entering at that Yellowstone Plateau and then exiting and getting warmer as it approaches the Idaho National Lab region, and then again gets colder and exits down at the Thousand Springs. And then this is another map showing the Idaho National Lab boundaries and the temperatures that have been measured by one of my colleagues, Travis McLean. And the temperatures vary in this area and represent different areas of upwelling of geothermal heat. And we want to understand those more and more so that we can figure out and better find the geothermal sweet spot for the Idaho National Lab. So here's a couple more plots showing some of the data that was collected for that study that you were just looking at. There are about 9 deep wells at the Idaho National Lab. One of them is down gradient, but these are geothermal gradient, or I guess thermal logs that have been done on those wells. Each one of those lines represents a different well. And you can see the temperatures on the top and increasing to the right, and depth on the left side increasing to the downwards. And so you can see temperatures on each of these wells increases until it reaches a point where it goes isothermal. Isothermal meaning it doesn't change with depth anymore. It has a constant temperature as it goes down. And once you get past that more or less straight up and down nature in the log there, you can see there's an inflection point, and where we understand that to be the base of the aquifer, where it starts warming up again, and temperatures are increasing. So some of those temperatures on the plot on the right go off the graph there, but it's really important that we understand that these temperatures increase quite rapidly after you exit the Snake River Plain aquifer. The Idaho National Lab has a geothermal resource research area that covers 110 square kilometers and is dedicated to geothermal research. This has been going on for decades, and much of the different geology, cultural, biological resources are well understood in this area. And another study done by a colleague, John Chervet, and others have identified this through the Snake River Plain Play Fairway analysis as a good area for EGS research. And this is a really important study that was happening about the time I was exiting school. But it has shown that there's a lot of potential both for hydrothermal and EGS geothermal. One of the studies I was involved with here back when I was an intern in 2015 was the sampling and analysis of hot springs in and around the Snake River Plain. So my colleagues, researchers at INL, and me as an intern went out and sampled around 100 different hot springs and wells in the Snake River Plain and around the Snake River Plain and nearby mountains. We conducted geochemical analyses, and we also did some geothermometry. Geothermometry just means taking a look at the fluids, the components that are in the fluids, and being able to calculate or back calculate what the temperatures would be in the subsurface based on what we see presently in those fluids. And one of the biggest tools that we've been able to develop and was recently published in 2024 is called the Reservoir Temperature Estimator. And this estimator takes into account the fluid chemistry, but also assumed mineral assemblages that are in the subsurface, and is able to give a more accurate temperature estimation for the geothermal resource. And the temperatures that we were able to find out in using that tool in this study ended up being 140 to 200 degrees Celsius, which is about medium grade heat for geothermal energy production. And that study is by our colleagues, Earl Mattson and others from 2016. This is an EGS slide. I think I'm going to skip it for now, just in interest of time. But we're involved in EGS research, trying to understand how to best produce geothermal energy from an enhanced geothermal system. An important piece of the puzzle here is public support. Geothermal does have strong public support in the region. It's regionally relevant and it's nationally deployable. We understand that the integration of other renewables is important and has been demonstrated with this technology. We are interested in linking it together with other thermal power generation, such as nuclear, fossil, and bioenergies. And then EGS, and what I'm going to get into now, GeoTES technologies are rapidly advancing and can also provide another integration with geothermal. So I just said GeoTES, and you see on the screen right now, geologic thermal energy storage, in short, GeoTES. I may use those interchangeably here. So the idea is that we're talking about storing thermal energy in fluid form in the subsurface for seasonal, diurnal, or dispatchable heat or energy production if it's high enough temperature. So here's a fun image, a little busy, but it has a lot of different information on here. And it's basically just to show subsurface utilization that we can take advantage of or do for decarbonization goals. As from a study, Kaminsky et al. From 2022, and various applications you can see here. There's nuclear waste storage. There's CCS, carbon capture and storage in saline aquifers on the bottom left there. Hydrogen storage is a big one you guys may have heard of. Compressed air energy storage, geothermal energy, heat and energy utilization. That's what I've been talking about on that far right. But what I'm going to get into now is more that middle section, underground thermal energy storage. So the call out on the bottom of that image, we have BTES, CAESC, compressed air energy storage, hydrogen storage, heat pumps, and then an interesting one, mine thermal energy storage, MTES. But essentially all of those are to show we have the option and the ability to inject fluids or gases into the subsurface and store them for later energy production or heat usage. And you're going to see multiple types of that depicted here in the next few slides. But again, the idea is to store excess heat underground for later use. That can be electrical use or district uses, heating and cooling purposes, basically. The benefit of this type of energy storage is that it's dispatchable, it's seasonal, it can be seasonal, and it can be flexible. It's in the subsurface, it's got a low footprint, and we don't have to worry about, large batteries that need to be built and maintained. So types of subsurface thermal energy storage include pit thermal energy storage, tank thermal energy storage, which are pretty simple and self-explanatory. There's a pit that you can put fluids in and store the heat. Tank, same, except it's contained. There's borehole thermal energy storage, where it's a closed loop system where you drill multiple boreholes and circulate fluids through those boreholes and use the ground's insulating capacity, but there's no interchange of fluids in the subsurface. There's aquifer thermal energy storage, which is the opposite of that. There is interchange. It's an open system. You inject fluids into the subsurface, let them sit, and then later pump them back out for energy production or heat utilization. And then reservoir thermal energy storage, which is what I've been most involved with over the last 4 years. And this is essentially aquifer thermal energy storage, except on a deeper and larger scale. Where we're talking about reservoirs so maybe oil and gas reservoirs, depleted oil and gas reservoirs, deeper saline reservoirs, highly porous, highly permeable formations that can store and receive fluids. So here's another depiction here. I should have switched about 30 seconds ago, so that explanation would have been a little more visible. But we've got aquifer thermal energy storage up in the shallower portion, where you've typically got a cold well and a hot well that you can inject the hot water and fluids into the subsurface, create your own little heat bubble, and later use those as you need them. And then the pressure balance is created on the cold side, and that cold side can be used again seasonally for heating and cooling purposes. Borehole thermal energy storage, you can see on the left, again represented kind of as a red blob, but it's essentially a bunch of boreholes that are drilled, and that heat can be stored in those boreholes. Now, reservoir thermal energy storage, as I said before, is deeper, larger, and can give a lot of grid balancing, grid flexibility type benefits. This type has not been demonstrated in the United States yet, but we are working on some projects that are working towards that. And I'll move on to a few others here to give you a little more background. Aquifer thermal energy storage, again, open system. It often designed as a doublet, one hot and one cold well. These hot fluids are injected in the summer and produced in the winter, and vice versa on the cold side. There's about 3,000 of these systems throughout Europe, most of which are in the Netherlands. And so we've learned a lot from our Dutch counterparts, and we want to apply those learnings to the deeper reservoir thermal energy storage, which I was describing. Most of these systems are on the lower temperature. We're interested in increasing those temperatures, especially for those deeper formations. The history here is depicted with this timeline, which I don't expect you to be able to read, especially in a short time, but essentially it started in China. GeoTES systems started in China, in Shanghai, and they've been developed a lot in the Northern Hemisphere, of course. But, over, the China, Japan, Europe, and some locations have been studied and tested in the United States, but currently not many. In fact, I think of only a few are operating in the United States, thousands of overseas. But again, the concept is that we're storing waste heat from, let's say, a nuclear source, a solar source, conventional energy generation, or some biomass energy. So we're storing that waste heat in the subsurface and utilizing Earth as a battery. So we've termed this the Earth battery or a geo battery. And it's important because it's a scalable renewable energy source. There's near zero emissions of CO2. There's no burning of fossil fuels, except if we're talking about conventional generation sources. But the fact that we can use the Earth as a battery to store and retrieve heat is really important, and it's something that we've been studying for close to 6 years now. There's low environmental impact. It can increase grid stability and help renewable penetration. It can help make better use of renewables when they're less needed. So if you've heard of the duck curve in California, essentially you've got a high amount of renewables that are being called on and cannot produce when they're needed most. And so the geothermal or geologic thermal energy storage can help combat that duck curve. It doesn't depend on different, it's not dependent on different types of thermal energy. It can be coupled with high-grade renewables and others such as nuclear. It increases plant efficiencies. It can lower utility costs and for communities and industrial processes. And a report that we've got that came out is actually coming up next. McLean et al. So McLean is my colleague at Idaho National Lab. We worked together with Berkeley National Lab down in California to study what we've titled here dynamic earth energy storage or geologic thermal energy storage to understand how this can be beneficial to the grid. We've looked at studies in Europe in more on the high temperature, so those above 40 degrees Celsius in the Netherlands and Germany. We've done some experiments and conducted some work looking at how scaling could be a problem and how to mitigate scaling in pipes and in your resource. We've done some geochemical modeling. We've also done hydrologic, chemical, and mechanical modeling, which I won't get into today, but really important stuff to understand how the ground's going to react and move as you start warming up temperatures. So if anybody's interested in looking at this report, I can send that over a little later. Just real quick, some of the lessons learned from Europe. This is a map showing mainly Germany and the Netherlands, and 10 of the systems that we studied. These systems varied in depths and rock types, and heat sources from cogeneration plants, solar plants, deep geothermal heat. Most of these systems have been built, used, and some of them have been suspended because of a variety of problems, which I'll get into next. So some of the problems that they've experienced were mainly geochemical and operational. So they had some mineral scaling that occurred when you start playing around with fluids and temperatures. Some minerals can drop out of fluids, some minerals dissolve into the fluid, and mineral scaling was a big problem for a lot of the systems that have been abandoned. Scaling occurs when the temperatures drop as you're producing the fluids, and they can scale in your topside equipment, and they can also drop out of fluids as they increase, such as the mineral calcite has retrograde solubility, meaning as that fluid heats up, the mineral calcite can drop out of solution and start scaling up the reservoir and pipes. So another few problems include redox conditions. If you introduce oxygen to a system that normally doesn't have oxygen into it, then you've got some problems with geochemistry and some corrosion that might occur. Mixing different fluids can create some issues. Biofouling, so in the subsurface, there's lots of microbes that exist. And when you start playing around with temperatures, that might excite them and it might increase their growth. And that could cause problems both on the top side and in the subsurface. Operationally, I've listed a few here. I'm not going to get into them too much, but essentially, depending on how the system operates, the heat that's delivered, these systems can react unfavorably. So some of the experiments we've done include raising temperature and pressure up to about 250 C and pressures of up to about 43 bars on crushed rock, and reacting those with fluids at those temperatures for months at a time. And so that's what we're looking at on the top right is our PAR reactor vessels that we react these rocks together with the fluids. And we've taken rocks such as the Weber sandstone in Wyoming and the lower Tuscaloosa formation from the Gulf Coast Basin in Mississippi. And we create a synthetic brine, which mimics the chemistry of the actual brines where these rocks came from. And we let that sit with the rocks and evaluate their scaling, the corrosion, and how the fluid chemistries change. And here's a few scanning electron microscope images showing the scaling that has occurred on these grains. I'm not going to get into the detail of all of these, but we've got calcite crystals growing in the top left on a sand grain that normally doesn't have calcite on it. Coating clays in the middle image, the two middle images and the bottom left, clays that are starting to grow on these grains that all result from increasing temperatures of these types of systems up to those 250 degrees that I was mentioning. Another bit of work I was involved with, I led this report that we created last year. Well, it was published last year, called Reservoir Thermal Energy Storage Benchmarking. And essentially what we wanted to do is to look at all types of energy storage and all types of thermal energy storage and figure out where reservoir thermal energy storage sits and how it can benefit the grid and our economies. So one of the images you see here is the LCOE, which is the levelized cost of energy, and our TES is sitting at the top of that, showing about 10 cents to 16 cents per kilowatt hour compared to other thermal energy storage options that I've described here. And the important thing here is that we learned that it has been modeled, at least because there's no operational systems yet. It has been modeled that these this type of energy storage can be beneficial and on the lower cost, as you see on that image. But the report has other things like capital costs, storage capacity, storage times, because, you know, is it days, is it months, is it seasons? So it's an interesting report. And again, if you're interested in learning more about it, I can send that over. I'm going to skip these next few slides, but essentially they're here to say we are working internationally with international partners in Germany, Switzerland, and Scotland to understand, you know, what these types of systems at high temperatures in depleted oil and gas reservoirs and abandoned mines, what that might look like, how that might operate, what might the effects be. And this is our project Vesta in Germany, in the upper Rhine-Graben, a depleted oil and gas reservoir. This one is the other international work that we've got going on, galleries to calories, storing waste heat from a data center in Edinburgh, Scotland, in abandoned coal mines beneath the capital there, and allowing it to transmit downstream to communities for district heating and cooling purposes. More recent work that we've been involved with here at the National Renewable Energy Lab and at Lawrence Berkeley National Lab, so a tri-lab partnership, is looking at the techno-economic analysis of geologic thermal energy storage. You know, how it looks technically and economically, how those can combine to help make this a viable option for energy storage in this nation. We look at potential estimation. I was involved in analyzing reservoirs across Texas and California to understand, you know, which reservoirs or formations might be most beneficial or suitable for this type of technology. And some of the modeling we've done have been using concentrated solar power and a Carnot battery, essentially using that excess heat from a concentrated solar plant, which you can kind of see the depiction of here. You got the parabolic solar collectors collecting heat from the sun, and then using that to be injected in the subsurface for later use. And this is a depiction of our partner's project in California, our partner Premier Resource Management. And again, that's the report name, that's the report cover. If you're interested, I can pass that on to you. So I'm going to wrap up real quick with carbon mineralization or carbon storage through carbon mineral carbonation is another way we talk about it. The idea is that we're talking about storing carbon from the atmosphere in the subsurface through mineralization and locking it up permanently so that it can't, you know, leak or move around in the subsurface. And you see an image here of a core of basalt or mafic volcanic rock with some white, crusty looking calcite crystals that are growing in that vug. And that's what we're looking for. That's what we want to do. So a bit more background: geologic sequestration of CO2 means we're taking CO2 from the atmosphere or from an industrial process, and we're storing it in the subsurface utilizing geologic formations. Oftentimes, depleted oil and gas reservoirs are used, or saline aquifers also are used in subsurface to receive CO2 injected in its supercritical state or in an aqueous state. Again, deep coal beds are an option. The research we're involved with are in mafic rocks, so in volcanic basalt rock. And so you see an image or a core box of an image of a core box on the top right. And this is a basalt rock from the Snake River Plain. You can see it's quite brecciated in places, and, you know, locking those pebbles, those cobbles of basalt in place are, you know, white veins of calcite. How did that calcite happen? Well, it happens naturally. There's CO2 in the subsurface being pumped up from various sources, and that CO2 passes through volcanic rock, and it can cause that CO2 or that calcite to drop out of solution and mineralize and lock up the CO2 for forever. And so there's a couple different processes that have been studied. Again, hydrodynamic trapping, which is traditional, you know, a seal trap where in the subsurface that CO2 is capped with a sealing geologic formation. There's solubility trapping, which you can basically inject CO2 into a fluid and it just stays or joins the fluid and stays in the aqueous state. But there's also the mineral trapping, which again is what I'm getting into, where we're talking about injecting CO2 into the subsurface and locking it up in a mineral form so that it can't move around. Why? Why do we care about this? Well, we want to decarbonize the nation, right? We want to we have these lofty goals of reaching net zero, and one way to do that is to store the CO2 that we're producing. And the one way that we've been focused on here at Idaho National Lab is in basalts. Major flood basalts exist around the world. They're important for the global carbon cycle. They've been implicated in past climate change events and mass extinctions. But you know, I'm talking about large basalt traps in Siberia, in the Deccan traps of India. Here in the United States, we've got a handful of them, the Columbia River basalts up in the Pacific Northwest, the Snake River Plain, and a variety of others in the mid-continent and southern part of the United States. Now, these are important because their chemical makeup makes them able to lock up CO2. You know, if you inject CO2 into a sandstone, it's not going to react the same way, and it's not going to lock it up as I'm describing now. And if we take only 3% of the basalt throughout the world and we're able to react it and it's suitable for injection, that's showing that we can store up to 100 gigatons of CO2 globally. So how does this work again? Well, you take basalt rock. On the left, you've got a calcium, magnesium-rich silicate rock, and those minerals are listed on the bottom here. Forsterite and anorthite are two of them, and you have those in the presence of a carbonated water, essentially a seltzer, and that seltzer, because it's low pH, is able to go underground. You inject it underground, it reacts with the rock and dissolves away certain types of anions, magnesium, calcium, iron, and those anions can later be dissolved and precipitated, excuse me, from solution to form calcite and other clays, and it locks the CO2 in mineral form. See, we're coming close on time. Again, mineral trapping in basalts. Here's a couple more examples. The core you saw in previous photo is there, but these other ones you're looking at. Oh, that's the, okay. So, some noise happening. I got it. The other two images you see here are some rocks that my colleague Travis McLean actually took and placed in a carbonated spring. If anybody's ever been to Soda Springs, Idaho, he placed them kind of secretly underneath a certain area of that spring so they wouldn't be messed with, and he let them react, and you can see the white calcite filling in the amygdals of that basalt. This is something that occurs naturally and worldwide, and what we want to do is understand how we can better take advantage of that and do it on a larger scale to help our decarbonization goals. Okay, so we're going back to the Snake River Plain of Southeast Idaho because we're currently doing a study with a large oil company, Chevron, that wants to understand and develop a pilot scale project to inject CO2 in southern Idaho and be able to demonstrate its feasibility in this case, a cold aquifer system. So again, we've got a map of southern Idaho. The blue blobs you see here represent the various eruptions from the Yellowstone hotspot over the last, 14 million years. Idaho National Lab located with the black outlines. That's where we're going to be doing the study. There's an image on the bottom right here of Idaho National Lab desert and the mountains that surround it. We've also got an image showing the basalts of the Snake River Gorge near Twin Falls, showing us kind of an analog of what we're going to be injecting into. And geologically speaking, again, the top, we see an image that we looked at earlier, a thick package of rhyolite ash flow tufts from Yellowstone style eruptions that are covered by a thick package of basalt or lava rock. Think of Hawaii, think of Iceland, that type of lava rock that's been erupted over the last 6 million years or so, that has insulated that deeper, hotter portion of the Snake River Plain. So the basalts in the Snake River Plain are pretty thick. I think up to about 4,000 feet there in the dark blue. These basalts are super important for us in this study because we need a thick package of basalt to allow the most reaction of this CO2 as we inject it. So here's a few images just to give you some context. Again, this is Shoshone Falls, Idaho, with the rhyolite ash flows represented kind of on the bottom up to midway in that image, and then you've got the black lava rock that caps that in the southern Idaho, and we understand this to be the case throughout most of the Snake River Plain. Here's another image of some rhyolites up in Yellowstone, showing they can be quite extensive and thick. There's an image of some ash flow tuffs, which we took in near Ryrie, Idaho. This is near one of my study areas. There's another image of the same basalt I think you saw before near Twin Falls, just showing multiple basalt flows that are kind of interlayered and stacked on top of each other, and they provide important pathways for fluid injection. The various fractures are really important as to understand where those fluids are going to go, how they're going to react. And I'll get into that in just a minute. There's another cliff of basalt down by Twin Falls. And you see a nice clay sediment layer down near the base of it. And then that's, I believe this is over in southwestern Idaho, near the Owyhee Plateau. Some hand samples of basalt here. I know we're running a little short on time, but essentially you've got a dictytaxitic olivine tholite basalt, meaning it's got a lot of plagioclase mineral, olivine and a pyroxene. So additional minerals in these basalts include iron oxides and basaltic glass, which can be the most reactive component of this rock type. On the bottom left, you see a microscopic image showing the kind of the interlaced nature of these minerals in the basalt. And we've also seen this on the bottom, on the right-hand side, before showing that calcite locking up some of these brecciated basalts. I really was rushing through that because I wanted to show you this. This is one of the coolest parts of the study so far. So we've got a stack of basalts here that we've conceptualized, or we understand to exist in the subsurface near Idaho National Lab. And the idea is those basalts are fractured, right? They've got brecciated zones at the flow bottom and the flow tops. And in the middle, they've also got fractures, but they're less fractured. There's a massive flow interior, which can be beneficial for fluid migration or transport. But what we're targeting for this study are the flow bottoms or flow tops. So the idea is that we're going to inject aqueous CO2, so basically seltzer water, like the stuff we're drinking tonight, and injecting it down into the ground and allowing it to react, to dissolve minerals, and then reprecipitate minerals, trapping that CO2. Sounds nice, sounds easy, but we've understood fractures to be quite complex in the subsurface. If we go back to some of those images, you can see the fractured natures of basalts can be complex. But the pilot that we're planning with Chevron is well informed because we've got over 1,800 wells that have characterized this region. The USGS has a well monitoring system that provides a lot of different core to us. I think there's close to 80,000 feet of core, I think is what the last number was, in their warehouse, that we can study and understand what the subsurface looks like. There's the productive sole source aquifer. The Eastern Snake River Plain aquifer can be, quite cold in places. And in the past, studies in Iceland have shown that hotter temperatures are a little more favorable. It allows for more quicker reactions to occur. But the Snake River Plain aquifer is quite cold. And so part of our job is to evaluate how that might change reaction rates, both dissolving minerals and precipitating out minerals. Let's see, I'll go ahead and move on from this. What we have done for this study are a lot of different types of analyses and modeling. But some of the stuff I'm highlighting here is our experimental work. So again, we took our reactor vessels, our PAR reactors. We reacted the crushed basalt rock with fluids in those cells. In this case, a dilute sodium chloride brine. And we did this at both temperatures, 20 degrees and 40 degrees Celsius. 20 being the highest that we might see in the Snake River Plain, and 40 degrees representing kind of a preheated nature of the subsurface. Throughout the study, we took fluids out in a time series and analyzed them to see how those fluids were evolving. And that helped us understand, where the system was going and how much, precipitation or dissolution might have been occurring. And then, we also took pre and post experiment solid samples, and I'll show you those right now. So here's an image of some grains of basalt from the ANL1 core. This is the SEM image of clean basalt samples or grains, both a coarser fraction on the left and a finer fraction on the right. You can see that their surfaces are quite clean and not a lot of mineral precipitation has been occurring. Now, after reaction, this is not those same grains, but the same, cells. Let's see. No, I didn't have noted on there what cell those ones came from. But here's an image showing different variety of minerals that have been precipitated on the surface of those grains. And some of those include iron, calcium, magnesium, titanium carbonate, which means when you hear the word carbonate, that means CO2 is locked up in those minerals. And I guess the spots that include that are 4, 5, 7, and 9 over here on the right. And I've got some more images here, which are pretty awesome. So here, spot 4 is the carbonate, iron, magnesium, calcium carbonate. And we got various silicates that have been precipitated as well from solution. The important thing here is that we've shown Chevron, and we are wanting to show and will show the public, is that these minerals can be locked up, or CO2 can be locked up in mineral form, even at lower temperatures like 40 and 20 degrees, as we've tested. Now, we will be producing more of these types of tests and results over the next few years with Chevron, and we look forward to learning more about how we can better decarbonize or lock up CO2 from the atmosphere. Now, some of the future directions we've got include, future research directions, I should say, include these 4 main topics, but we've got more in the pipeline. GEOD stands for Geothermal Energy from Oil and Gas Demonstrated Engineering. Essentially, DOE, or the Department of Energy, wants to marry the oil and gas and geothermal industries and use technologies, knowledge base, and know-how, and kind of bring us together so that we can learn from each other and apply technologies to advance geothermal energy. That is in its first year right now, and it's going to happen for the next 4 years with more and more funding coming from DOE to help demonstrate technologies and grow the geothermal industry. Additionally, my colleagues and I are interested in critical and strategic minerals and materials. Now, these are non-fuel materials, elements, and substances essential to technologies in the clean energy, aerospace, electronics, and defense industries due to their unique properties. They're super important to the government, to the industries that are producing these technologies, and we need to be able to find ways to extract them from various sources, whether it's hard rocks or fluids. And so we're conducting many types of analyses on how best to do that and how best to bring those critical minerals to the market and be more domestically sustainable. 2 other topics include lithium extraction from geothermal and oil and gas brines. We've got 2 projects, one in Louisiana, one in Utah, where we are evaluating lithium concentrations in those brines from various formations. the Paradox Basin of Utah and the Smackover Formation of Louisiana and Arkansas. We're also interested, in fact, I just got the contract signed yesterday for a geologic hydrogen resource evaluation in the Snake River Plain. And essentially this is to look at how the earth is producing hydrogen and is it viable to produce, at least in southern Idaho, at commercial quantities. So the idea is that serpentinization is a process in the subsurface where water reacts with mafic minerals or ultramafic minerals, and in the process releases hydrogen from those minerals. And so that hydrogen can be trapped and accumulated in certain locations and is very, has been shown to be, have high concentrations in areas like the Snake River Plain that has a high concentration of basalt or mafic type rocks. So those are just some of the areas that we're interested in. I know I covered a lot of material today and kind of skin deep on most of it, but I appreciate your attention and I thank you for your time. Any questions? Yes.
So, Trevor, when you talk about using basalt to, when you talk about using basalt to trap the CO2, do you have to frack the basalt, or are you just targeting these breccia layers that have more surface area available for conversion into calcite? Does that question make sense?
Yes. Yes, it does. The latter is the answer. We don't have any plans to frack the basalt. In fact, we don't want to. That has lots of different issues, especially when you're talking about near the Idaho National Lab where there's reactors currently operating. So we don't want to fracture the basalt. We're targeting natural fractures and brecciated zones like I described earlier. Oh, yeah, go ahead.
Okay, we've got a Zoom question here. I'm gonna stand close to you so people can.
Oh, careful.
So, does Montana have high EGS potential? I see it's less hot, orange, but perhaps it's still feasible there?
I can't speak about Montana specifically. I will say EGS has potential everywhere. How to access the rock deep enough to get to those temperatures? That's a good question. The DOE has projects in Utah. Industry has projects in Utah. I know there's been EGS studies done elsewhere. I'm not aware of any that have happened in Montana, but our motto at DOE is geothermal anywhere. And so just, who wants to pay for it to drill to those depths? That's the hard part to find.
Are there geothermal plants where they make the pressure really high so that calcium carbonate doesn't precipitate in the pipes? Like a few thousand pounds, maybe that's way too expensive.
Yeah, so the question is about pressures at geothermal plants to keep mineral scales in solution so that it doesn't scale up. I believe so, but when we're talking about pressures that high, those can have deleterious effects on piping and surface equipment. So I can't speak to any pressures in specific, but I think more treatments that occur in geothermal plants include chemical treatments and well workovers. Essentially, they shut wells down, come in and blast them out, grind out the scales mechanically, get rid of the scale. Yeah. Yeah, that's one technique. Yeah. Oh, it's not good. Yeah. Yeah, you want your plant online as much as possible. And so if you shut down wells, that's bad for your efficiencies. So yeah, you raise a good question. I mean, I can't speak to the pressures, but I'm sure they've evaluated those things to some degree. So sorry to give you a non-answer, but that's all I got. Yes, Mike.
In geologic hydrogen resources, I mean, it would seem like if it was easy to do, we would have been doing it all along. Since hydrogen is such a great fuel, it burns basically and makes water. And there's problems with storage and transportation. But it would seem like production is the real hurdle, or is that not true?
Yeah, that is true. Hydrogen is a slippery molecule. It's the smallest, right? And so if you try and find and capture hydrogen, it's some of the hardest that you can find, capture, transport, and utilize. But the study that we're interested in, and what USGS and others are interested in, is this natural production of hydrogen, which has not been studied extensively. They know it exists in oil and gas fields. They know it exists in geothermal fields, but it's natural production that we can't see, smell, or know about, right? Is what we're interested in evaluating. In many different types of many parts of the country, but our specific study is in southern Idaho. So hopefully it's not hard, but we're gonna evaluate it. We're gonna sample it and understand it. Yep. Get you the mic.
So USGS recently published a paper about lithium from geothermal and oil and gas brines. They focused on southern Arkansas and northern Louisiana.
Okay.
And they said that there's enough lithium in the Smackover formation to give us all the lithium we want. The critical thing is, instead of having a surface mining operation that's very disruptive, you can just drill wells, produce the brines. So what has INL, have you been involved with any of that assessment?
With that particular study, we were not involved, but the fun thing is we do have studies right now. They were just signed a couple months ago for the Smackover in Louisiana specific, because if you look at a map, a lot of the assessment ends at the Arkansas-Louisiana border, because the Smackover has been studied there most. But our goal is to understand in northern Louisiana what the Smackover lithium concentrations are, because right now it hasn't been studied or reported, at least from many of those oil and gas fields. Again, we have another study in the Paradox Basin, Utah, to do the same thing. Another oil and gas field that has lithium concentrations. How much and how sustainable the extraction of that is. That's part of our study. Another big study that was done was in the Salton Sea in California. Our colleagues at Berkeley National Lab, they conducted a really extensive study for the Salton Sea. And I think that plus the Smackover are our two largest sources of aqueous lithium. And I think you're right. I think producing from natural brines, lithium directly is a much more sustainable, much more environmentally friendly way of producing lithium that we all want and need for batteries and other purposes. So thank you. Any others? All right.
I got a couple,
Oh.
sorry, got some more Zoom questions.
Oh, I thought I was done.
Yeah,
No, not that.
The Zoomers got me.
Zoomers got you.
All right.
So have there been preliminary estimates for the cost of extraction of lithium from solution?
Yes. In fact, that Salton Sea study that I just referenced does that. And it studied how sustainable it is. And part of that calculation is the cost. And I've been involved in evaluating direct lithium extraction technologies and what they look like, how functional they are, and how much they cost. So those studies have been done. I have not produced those studies, but I've seen the technologies that have, and they exist. And I could look some up and find them for the questioner. Laurel, is that her name?
This was
needed.
Dado.
Oh, Dado. Okay, cool. Anyway,
We'll get the chat down.
yeah, that's fine.
Yep.
Thank you.
Okay, I think we should probably wrap it up now.
Yeah.
All right.
Thanks, everybody.